we have a wonderful test to look at. Calculus 2, Exam 1. We're talking applications of integration. And that's what we're talking about, applications of integration. And there's a lot of things we can say. 10 problems worth of things we can say. 6 multiple choice, 4 workout. A lot of this will be saying, hey, do we understand how to set things up? Now, as always, make sure we put our name on it because we want credit for our work. And so, with that, we're ready to begin. And we'll start off with our multiple choice. We just have to find the right answer, right? That's all we have to do. And so we begin with number 1. Where does the parametric curve have a horizontal tangent line? Now you'll notice they're stressing horizontal, like they're putting that bold. And so that's just saying, hey, make sure you pay attention to that. So what does that mean? Well, here we're going to look at, we have our plane. Now a horizontal tangent line, that would look something like this, right? Flat, going straight across. And what does this correspond to? Well, if we think of our slope, for parametric curves, our slope becomes change in y over change in x. Well, horizontal tangent line is when you get y prime of t equals 0. Now, be careful, because we can also talk about vertical tangent lines. And what would that be? Well, vertical tangent line is when x prime of t equals 0. So we say, all right, we know what we need to do. Since we want horizontal, we take our derivative, we set it equal to 0, and we solve. And all right, well, let's give it a try. So we take our y prime of t, that would be 4t plus 4. We set that equal to 0, solve for t. So you subtract 4, divide, and you say, that says t equals minus 1. I say, I don't see a minus 1 here. Well, you shouldn't, because this is t. We want x's and y's. So now what can we do? Well, we take this minus 1 and we plug it in. So for example, x of minus 1, well, minus times minus 1 squared, well, that's going to give us a net of a minus 1. 4 times minus 1 is minus 4, and minus 3 makes minus 8. Well, that's not true, that's not true, that's not true, that's not true. Aha, must be B. We'll go ahead and check for the y. We don't need to, but might as well. 2 times minus 1 squared is a 2. 4 times a minus 1 is a minus 4. And a minus 6, 2 minus 10, minus 8. All right, excellent. Double checked. And what would have happened, by the way, if you had taken x prime of t and set it equal to 0? Well, you would have gone t equals, looks like 2. And that would have gotten you, I believe the answer is part C. So pay attention. These words matter. All right. Number 2. The region in the first quadrant bounded by the curves y equals 1 minus x, y equals 1, and x equals 1 is rotated around the x-axis. Well, let's actually draw this because it's hard to see what's going on without a picture. Now, y equals 1 minus x. It's going to intersect here at 1 and have slope minus 1. So this is our y equals 1 minus x. Y equals 1 is up here, and x equals 1 is right there. And so we have a triangle. All right, so here's our lovely triangle, and it's rotated around the x-axis. Well, x-axis, that's downstairs, so we're going to rotate it here, around the x-axis. Good, good. Now we have a picture. Which of the following integrals gives the volume of the resulting solid when using the washer method? Now notice it doesn't say we actually have to compute. It just says we have to set it up. So we got to make sure we get our setup correct. Now, how do we set things up? Well, one of the things is we have to decide how we're integrating, but we don't even have to think very hard. Like when I say how are we integrating with respect to x or with respect to y? But notice all of these integrals are with respect to x. So it says, oh, we're definitely integrating with respect to x. So what's the thought process? Well, break things into pieces. So you say, oh, I take a small slice. So here's a small slice with respect to x. And we would spin it. And when we spin it, what do we form? Well, we form a washer. So, okay, so how do we find the volume of a small slice? Well, we think of it as a washer is a big circle minus a little circle. So we say pi times the big radius. Now the big radius is from the farthest point out. So the big radius here is 1 squared. Subtract pi times the little radius, 1 minus x squared. Now that's the area of a cross section. Multiply that by the width. That's the volume of a cross section. Now you add up the volumes. And we're going from 0 to 1. So we say, great, that's what we're looking for. And that's not what any of these say. But there's certainly a case that we can rewrite. So we say, all right, what can we do? We can pull out a pi. That's not so hard. That's easy as pie, right? So we can pull a pi out. And so we say, okay, so this becomes, we have a pi, integral 0 to 1. We have 1 squared, which is 1. And then we have 1 minus x quantity squared, 1 minus 2x plus x squared. And don't forget this minus sign in front of it. That is going to distribute through. So it's going to become a minus 1, a plus 2x, and a minus x squared. Well, the ones cancel. That's pretty straightforward. And what do we see? Well, we have a 2x minus an x squared. And we say, so it's pi integral 2x minus x squared. That's E. And there you go. There you go. Now, on a side note, there's a very tempting one. This x squared minus 2x. That's if you forget to distribute your minus sign through. So, be careful. Be careful. So how about some of these others? Well, they come from various things. But yeah, this is the one I think is most dangerous. But all right. On to our next problem. Number 3. Find the force of water on one side of a fish tank full of water if the dimensions of that side of the fish tank are 1 foot tall and 2 feet wide. The density of the water is 60 pounds per cubic foot. Now, 60 is actually not quite right, but it's a nice big number. So how do we find force, or if you like, fluid force? Now the idea is the following. So here we have our 1 foot tall, 2 foot wide fish tank. And what we're going to do is we're going to add up the force as we go up and down. So we have a small cross section. And for convenience, it's good to pick a good place for 0. And for 0, you want 0 to be where the top of the water is. And then going down, so this would be 1. So the fluid force, what we do is we're going to add up, start to stop. It's going to be our density times our area times our depth. Those are the 3 things: density, area, and depth. Now, I think I got them slightly out of order, but that's okay. Those are the 3 things we're looking for. We know our density is a constant, 60. Great. Our depth, well, that's how far down we are. So let's call this y, because it's a vertical thing. Y. Now, what's our area? Well, our area, if we're just taking a small slice, it's always the same width across. And so it's 2, and then the height is dy. So this is 2 dy. And so We're almost there. We're going from 0 to 1. So this becomes integral 0 to 1, 120 y dy. Well, we're almost there. What comes next won't surprise you. We integrate. Okay, what's the integral of y dy? 1/2 y squared. So this is 60 y squared. Evaluate 0 to 1. And now, plug in 0, you get 0. Plug in 1, you get 60 times 1. So we get 60. So the answer is 60, and our force is pounds. Well, we don't need to worry about the units. They're all given to us. And there's the answer. All right, good. Now, by the way, there's a lot of formulas to memorize. This is a good time to say, know your formula sheet. If you know your formula sheet and you know how to use it, it makes this test so much more fun. And if you don't know your formula sheet and you don't know how to use it, this is going to be a very aggravating test. So, okay. All right. Back to our regularly scheduled exam. Number 4. Find the length of the curve defined by f of x is 2/3 x to the 3/2 on the interval from 0 to 3. Now, I don't know exactly what 2/3 x to 3/2 looks like, but, it's not too hard to see. At 0, it's 0, and then it's going to go up. Okay, so we're going over to here. All right, now what tool do we need? Well, length of curve. And length of curve comes in 3 flavors. You have length classic, y is a function of x. You have parameters, and you have polar. Now for us, we're in length classic. And so for that, we say, okay, length is you're adding up a to b, the square root 1 plus the derivative squared dx. All right, so that's our formula if we have it as y equals f of x. All right, so what do we need to do? Well, we need to figure out what these pieces are in particular. Well, a to b, that's given, right, because we're told 0 to 3. 0 to 3. Square root of 1 plus, now take this derivative. And now we have a pretty good idea of why they put 2/3. Because when we take the derivative here, the 3/2 comes down. So we have that 2/3. Then we're going to bring the 3/2 down. X to the 3/2 minus 1 is 1/2. Well, the terms in front cancel. And so this becomes integral 0 to 3, square root of 1 plus x dx. Or, if we were to write this in a more calculus-friendly way, integral 0 to 3, 1 plus x to the power 1/2 dx. Now, this is a pretty straightforward integral. You can do a u substitution if you need to, u equals 1 plus x, but we're really hoping, fingers crossed, that you're at the point where you're like, oh, I can handle a plus 1 on the inside. I just sort of like, it comes along for the ride. So this would become the following. You would add 1 to the exponent, so that would come to the 3/2 power, and then you divide by the reciprocal of your exponent, 2/3. And we need to evaluate from 0 up to 3. So we need to plug in 3. 1 plus 3 is 4, so we have 4 to the 3/2. And when we plug in 0, you don't get 0. What do you get? Well, you get 1 plus 0 to the 3/2, which is 1 to the 3/2, right? So oftentimes we get 0 so often when we plug in 0, we may forget to do that. So be careful. It's a very easy mistake to make, and we don't want to lose points for an easy mistake. We don't want to lose points at all, but we don't want to lose them for silly things. All right, now let's think of 4 to the 3/2. One thing we could do is we could cube 4 and get 64. Square root of 64 is 8. Or, hear me out, another thing we do is say, well, instead of cubing, making it big, and square rooting, making small, let's first square root, make it small, and then we'll cube, make big. So square root of 4 is 2, and then 2 cubed gives 8. So the punchline is this is 8, And then we're going to subtract 1. So this is 2/3 times 7, which is 14/3. And there we go, 14/3. And hey, check it out. Check, check, check. Check it out. It's an option. All right, good, good. Well, let's keep going. To number 5. Find the surface area obtained by rotating the parametrically defined curve x equals x equals cosine t and y equals sine t from t equals 0 to t equals pi fourths around the y-axis. Okay, so this is parametrically defined, so that's good to keep track of. Now, we don't technically need to know what this curve is, but I think we might recognize it. X equals cosine, y equals sine. It's a classic, one that we've seen for years. What is it? What curve has x equals cosine, y equals sine? It's the unit circle. And in particular, at time 0, you're over here at 1, 0, and then we're going to come up halfway. So this would be here at time pi over 4. And so that's what we're going to be rotating, and we're rotating it around the y-axis. So in particular, we have a piece of a sphere. That's what we're doing. We're finding the surface area of a piece of a sphere. So, how do we do this? Well, the good news is we have a formula, right? How do you find surface area? So surface area is you add up little pieces. You say, okay, well, how do you find the pieces? It's 2 pi, the radius, length. So that's what we need to figure out. Now, the bounds will come from the bounds from the parametrization. So this is going to be integral 0 to pi over 4. The 2 pi will be 2 pi. Okay, all right, I see what they did there. Nice. What's the length? Well, the idea is we're breaking this into little tiny pieces. So here's a little tiny piece, and we're saying what's the contribution of that to the surface area? So the length is this distance to where we spin. So how far away are we from the y-axis? X. This is one of those things where it sort of like flips it around. Like, oh, if I want to know how far I am from y, I use x. If I want to know how far I am from x, I use y. And so because you have that sort of strange switching, it's easy to make that mistake. And so we say, okay, so this is our x of t. This is our radius. And so what is our radius? It is cosine t. All right, so I'm just going to put x. So here's cosine t. Now, length. Aha! This gets back to sort of our length problem where there's length comes in 3 flavors. And we talked about the previous one was like length classic. And here we're in length parametric. And so, okay, so how does one do length parametric? Well, it's the square root of x prime squared plus y prime squared dt. So this is the little bit of length. Well, for us, this is the square root of x prime squared. Well, x prime would be negative sine. And if you square that, that negative goes away. So sine squared. Y prime, derivative of sine is cosine. And if you square that, you get cosine squared. Now, what's another name for sine squared plus cosine squared? 1. And so, this becomes very nice. It becomes dt. And that's the advantage of, working on the unit circle, is you have very nice pieces here. So this, we'll go ahead and write this down. This is x prime squared plus y prime squared dt, which becomes dt. So that's our computation we have to carry out. All right, well, the end is near. We see where we have to go, but of course, we have to get there. What's the integral of cosine? It's positive sign. So we get 2 pi sine of t from 0 to pi over 4. If you plug in our sine of pi over 4, that would be square root of 2 over 2. And if you plug in 0, you get 0. You say, oh, well, okay, the 2's cancel. So we should end up with square root of 2 times pi. And C. There we go. All right. Nice. Nice. Woohoo. All right. So that's number 5. And that brings us to number 6. Our last multiple choice. Oh, they go by so quickly. All right. Which of the following graphs represents the polar curve r equals 2 plus 2 sine theta? And they gave us some graphs, and they have these circles. Now, they didn't quite explain the circles. What does each circle represent? My guess would be to say it looks like these are radiuses. And so each circle probably is like a distance of 1. But we don't need to know that. What do we need to do? Well, we just need to have enough information to say, is this or is this not something that works? And here's what I recommend. Choose some very simple angles. So let's try, for example, r equals 0. No, sorry, not r equals 0. Theta equals 0. Why that? Well, that is the direction if we go in the positive x direction, right? So this is theta equals 0. Now, when we plug in theta equals 0, what do we get? Well, that leads us to r equals 2 plus 2 times sine of 0. Well, that's 2 plus 0, or 2. So that says if I move in the positive x direction, I should have a point roughly 2 out. So now, this one, okay, that looks like it could be. That's a potential. This one, there's nothing. We don't hit anything in the positive x direction. Here, okay, maybe we hit something. Here, nothing. Here, nothing. We're just missing. All right, well, what else can we try? Let's go try, I'm looking at these and thinking, what's a direction that's very different? Maybe let's try pi halves. That would be straight up. Okay, so when we plug in pi halves, what do we get? Well, when we plug in pi halves, we get the following. Well, we're going to get 2 plus 2 times sine of pi halves. Sine of pi halves is 1. So this is 2 plus 2 equals 4. So that says we should have something 4 away. So not only will we have something, it's got to be twice as far out as when we went in this direction. Now notice we do hit something here, but it's the same distance. So it's not twice as far out. But here we look, say, oh yeah, we hit something, and it's about twice as far out. And so we say, whoa, wait a second. We've eliminated everything else, so it must be what remains. Remember, when you're doing multiple choice, you don't necessarily need to find the right answer. It's enough to say all the others are wrong. So you can say, well, look for things that don't work. Look for how the others break down. And that can be a great strategy for solving multiple choice. All right, well, that leads us to our workout problems, our write-out, long answer. And for these, we've got to show more detail. We really do have to say, why is it the way that it is? And so, all right, that's our goal. And, well, let's begin. Number 7. Let R be the region bounded between the curves y equals 3x squared minus 4x and y equals minus x squared plus 4x. Find the volume of the solid generated by revolving R around the line x equals minus 1. And then they provided a picture. Now, they didn't explicitly say that the picture is the problem, but I'm going to trust them. I don't think they're just going to randomly throw a picture here. And they say, okay, well, here's this line. So this line must be our x equals minus 1. We also have two parabolas. You can see they're parabolas. They have x squared. And you might say, well, which one is which? Well, let's start with the bottom one. Notice it's a parabola that opens up. It's opening up, up, up. It's our moment. Da, da, da. Oh, wait, no, sorry. Something else. If you have a parabola opening up, what's true about the x squared term? It's positive. It's the optimistic parabola. And notice this has a positive x squared term. This one has a negative. So the bottom part, that's our 3x squared minus 4x. Okay, that's our bottom piece. And then our top, that's the other one. And so we say, okay, and let's check. And again, it's a parabola. You'll see this is a parabola that we would think of as opening down. So again, negative value in front of the x squared. So that's our top. All right. So what do we need to do? Well, because of the way the problem is given to us, y as a function of x, it's very suggestive. Integrate with respect to x. In other words, don't add work if it don't need to. And we say, well, okay, since we have it in terms of x, our plan, integrate with respect to x. And all right, well, that's good to know. And okay, well, if we're integrating with respect to x, we're going to think about taking our slices as up and down slices. And then when we spin, what shape do we end up forming? What do you see? Take a slice, right? Because this is integrating with respect to x. And when you spin, we get a shell. Okay, so this is a question about shell method. And, well, we have most of our pieces. We know how to figure the height. That's the difference. We know where we're spinning around. The only thing that we need to figure out is where do we start and stop. Okay, so we need to find where these two parabolas intersect each other. All right, so let's do that. So where do our parabolas intersect? We set our minus x squared plus 4x equal to our 3x squared minus 4x. We'll move things across, and that becomes 4x squared minus 8x equals 0, right? Because I add x squared, I subtract 4x. And that becomes 4 times x minus 2 equals 0. Leading us to x equals 0 and 2. So here's 0. And over here, there's 2. And you can just sort of do a quick sanity check. Minus 4 plus 8 is 4. 12 minus 8 is 4. All right, so now we have our intersection points. That tells us our start and stop. So we're ready. All right. Well, what do? We write down our formula. So our volume, because we're after volume, is add up, start to stop, 2 pi. We have our radius, our height, and our thickness. Those are the pieces that make up our shell method. So let's talk about all of these pieces. Well, A and B are the start and stop, 0 and 2. Okay, that's no problem. 2 pi is 2 pi. The radius. Now the radius is, given that we have a slice at x, how far is it to where we spin? So this is our radius. How far is it from an arbitrary in x to an x equals minus 1? So what's that distance? Well, it would be x subtract negative 1, which becomes x plus 1. right? And you can see it here. This is x, and this is 1. X plus 1. All right, now we get to the height. All right, so how do we do height? Well, the height is up and down. This is the height, h. So we take top minus bottom. So we're going to take minus x squared plus 4x. That's our top. Subtract our bottom, 3x squared minus 4x. Finally, what's our thickness? In our case, our thickness, we're thinking about it as just sort of our small change, right? This is our thickness here. Small change in what we're integrating with respect to, that's our dx. All right, so those are our pieces, our bounds, our radius, our height, our thickness. And now we just need to clean it up and carry out the computation. Well, let's clean this part up. 4x minus 4x is 8x. Minus x squared minus 3x squared is minus 4x squared. You might say that looks very familiar. It is. It's the same thing you did to find intersections. And all right, now here, instead of trying to factor, you want to do the opposite. You want to expand. All right, so we're going to multiply this by our x plus 1. So we have a 2 pi. We'll throw that out in front. 0 to 2. X times 8x is 8x squared. X times minus 4x squared, minus 4x cubed. 1 times 8x, 8x. 1 times minus 4x squared, minus 4x squared. All right. And, well, we can do a little bit here insofar as we have 2 x squared terms. So let's see. I'll go from lowest. So 8x squared subtract 4x squared would be plus 4x squared. And then we're going to subtract 4x cubed. All right. And we're in our home stretch. We do have to find it, right? We can't just stop. We need a number. This is not just a setup. It's a find. So we have to carry out the computation. All right, so we have a 2 pi out in front. And, well, fingers crossed, integral of 8x. Well, okay, add 1 to x. So this power to get x squared divided by 2, 4x squared. Add 1 to the exponent, divide. That would be 4/3 x cubed. Add 1. To the 4th power, divide by 4, minus x to the 4th, and evaluate from 0 to 2. Now, the good news is 0 is really easy. 0, 0, 0. Pow, pow, pow. Gone. Whew. Okay, so we've got to plug in 2. So, this is 2 pi. 4 times 2 squared. 4 times 4 makes 16. Plus 4/3 times 2 cubed. Okay, well, that'd be 4/3 times 8. That's 32/3. Minus 2 to the 4th. All right, 2 times 2 times 2 times 2 is 16. They're like, almost like they want it. The 16s cancel. That's going to make it really easy to simplify. We're almost there. 2 pi times 32/3 leaves us with 64/3 pi. Oh, nice. Nice. We did it. Good job, us. We made it through our first workout problem. More to come. So let's go on to number 8. Find the center of mass of the thin plate enclosed by the curves y equals 1 and y equals x squared. And again, they're giving us some pictures here. So let's just assume that these pictures are accurate. Y equals 1 is this top part. So here's y equals 1. And then y equals x squared is this bottom part. Okay, so here's y equals x squared. All right, that's down the stairs. And there's the density. The density is x squared. Now, what does that tell us? Well, it tells us that in terms of the region, that the density gets, well, it gets more dense. I want to say the word thicker. There's higher density the further out you go. So it's pretty sparse near the axis, but then it starts picking up. So there's lots of density towards the edge, and but again on the other side, again lots of density towards the left and the right. Well, it's a two-dimensional region. So when we talk about center of mass, that's a location. In 2 dimensions, that means we need a point. All right, so what can we say about our center of mass? Well, we can get one of the coordinates for free. Which coordinate is a freebie and why? The x-coordinate. The x-coordinate is 0. Why is the x-coordinate 0? Well, because we have symmetry. That's right. So we don't even have to think about what's going on in terms of the x direction, because what's happening? Well, look at the picture. It's symmetrical with respect to 2 things, the shape and the density. So that is to say, you can almost imagine like take a spatula, pick it up, flip it over, put it back down. You wouldn't be able to tell that you did anything. And so this idea of picking up, turning it over, and putting it back down says, oh, what you did is you twisted around the y-axis. And so we know that the center of mass has to respect that symmetry. So it has to be on the y-axis. So we get 0. And you need to include that point. And indeed, just even saying, hey, it's center of mass is 0 by symmetry, that's like 1 or 2 points. And we love our points. We want to get all our points. All right, well, that still leaves us with the y-coordinate. So how do we find the y-coordinate? That's going to be more work. We know for sure it's going to be somewhere between 0 and 1. I suspect it's going to be closer to 1 than 0. The reason I say that is I'm thinking about where we have more mass. We have more mass over in these right endpoints, and they're higher up. So it should be somewhere here-ish. That's not an answer, but that's what we're expecting, closer to 1 than it is to 0. Now there's a nice formula, and I can give you a moment to think about it. All right, it's the moment with respect to the x-axis, and then divide by the mass. Okay. All right, so we need to carry out this computation. All right, well, let's start with the mass. That's not so hard. What is mass? Well, if we were doing mass, the way we find mass is we're going to add up, start to finish, our density, and then times by our area. So for us, we're going to go from -1 to +1. You can see where we intersect at plus -1. So we're getting up from -1 to +1. Our density is x squared. Now what's our area? Well, when we take a small slice here, our area is from the top, which is 1, minus the bottom, minus x squared. So that's the height, and then our width is dx. So height times width. All right, great. So we can do a few things. One is we can use symmetry to make our computation easier. And say, okay, let's look. It's even, and so we can just double the integral from 0 to 1. So this is evenness. And now, if we distribute through, we'll have x squared minus x to the 4th dx. All right, so this becomes 2. We integrate 1/3 x cubed minus 1/5 x to the 5th. Evaluate from 0 to 1. And if you plug in 0, you get zeros. That's why we like to use symmetry, because we get more zeros. 0 is a friend. It's a wonderful ally. And so when you can get it, use it. All right, when you plug in 1, okay, this becomes 2 times 1/3 minus 1/5. Or if you get common denominator of 15, that's 5 over 15 minus 3 over 15. 5 minus 3 is 2. 2 times 2 makes 4. So that's 4 over 15. So that's the mass. Is that the coordinate? No. No. But it's the denominator. So that's something. 4/15. Now we still have another part. You know, you're probably thinking like, just when you thought you ran out of fun, there's more fun to come. Okay, so now we got to do the moment. Now the moment, it's very similar to the mass. So we can adapt a lot of it. So our moment, A to B, we're going to add one more thing, which is a distance. So it's distance, density, area. Okay. So, same A and B as before. -1 to 1. Distance. This one we got to stop and think about for just a second. So think about this rectangle, right? Because we always think about a small piece. For a small piece, where's the center of mass of a rectangle? It's in the middle. Well, where is that? It's halfway between the top and the bottom. So the distance to the x-axis, and I forgot to put m sub x for the one with respect to x-axis. So this is our distance to x-axis, just to be very explicit here. So that would be, find the middle. So that, to do that, you add the top and bottom and divide by 2. So it's 1 plus x squared over 2. And then, well, everything else comes along. You still have that x squared for your density. Your area is still 1 minus x squared dx. And we have our setup. Now, we'll take advantage of symmetry again, right? Because everything is even. There's beautiful symmetry going on here. So we can pull out the 1/2. But then we're going to add a factor of 2 by symmetry. And we're going to go 0, 1. Okay, so we're using symmetry. I'll mark even. If you didn't use symmetry, don't worry. You still get the same answer. The only thing that symmetry gives us is a little bit easier computation for evaluation because we get to use the 0. So if you don't see symmetry, don't panic. You're fine. You're fine. All right. Well, let's multiply. Now, we can actually do it if we think about it the following way. So we have a half x squared, 1 plus x squared, 1 minus x squared. And the 1 plus x squared times 1 minus x squared, that's pretty easy, right? A plus b, a minus b. So this part would be 1 minus x squared squared, x to the 4th. Right, just check it out. 1 minus x squared plus x squared, get the cancellation, minus x to the 4th. And then take the x squared through. So that, when we multiply it out, becomes x squared minus x to the 6. Okay, so that's the integral we have to perform. All right, well, that is the 1/2 and 2 cancel. And so we end up with 1/3 x cubed minus 1/7 x to the 7th. And we're going to evaluate from 0 to 1. 0's our friend. Goes away. So you plug in 1. 1/3 minus 1/7. And okay, common denominator would be 21. 7 over 21 minus 3 over 21 will get you 4 over 21. All right, so that is the moment. Now, does that go there? No. No. It goes here. It's part of the computation for y bar. But now we're in our last few steps. So what do we have here? We have 4 over 21. Then bring this by flipping it over. It'd be 15 over 4 if we flip it, bring it upstairs. The 4's cancel. We have 15 divided by 21. Well, those have a factor of 3 in common. Okay, so 15 over 21, we can write this as 5/7. And so that is there. Now, does that match with what we expect? Definitely has between 0 and 1. Check. And we said it should be near to the top. Well, 5/7 is closer to the top than it is to the bottom. So it's a reasonable answer. And I think it's actually a correct answer, which is even better than being reasonable. Whoa! It's like reasonable plus. All right. Well, let's keep going. Number 9. Find the area enclosed by r equals 2 sine 3 theta plus 4 in the first quadrant. And oh my gosh, tons of pictures. They're just like throwing pictures at us. Okay, now, one thing they didn't say, but we can get from context, what kind of problem do we have? This is polar. How do we know it's polar? R's and thetas. All right, so we have to do area in polar coordinates. So that's fine. And the good news is there's a formula for that. So what's our formula? We have that the area is add up from start to finish. And I'm using alphas and betas because we think of these as angles. 1/2 r of theta squared d theta. So 1/2 r squared. Okay, now for us, well, we're in the first quadrant. So what are our angles involved in the first quadrant? The x-axis would correspond to the angle theta equals 0, and the y-axis is pi halves. So those are our bounds. We're going 0 to pi halves. So we say, all right, great. That gets us started. And so we write that down. 0 to pi over 2, 1/2, and now r's right here. 2 sine 3 theta plus 4 squared. All right, well, let's clean up the inside. 0 to pi over 2, we have a 1/2. We square this, well, that'll be 4 sine squared of 3 theta. And, right, a squared, and then 2ab. So 2 times 2 sine 3 theta times 4. So, well, go ahead and write 2 times 2 sine 3 theta times 4, 2ab, plus b squared, 16. All right, well, if we multiply the half through and clean this up, we say, okay, 1/2 times 4 gives us 2 sine squared of 3 theta. And then 1/2 times that 2 times 2 sine 3 theta times the 4. That will give us to 8 sine 3 theta. And 1/2 times 16 gets 8. All right, good. Now let's just check to see where we're at. We have a couple of pieces. And so when I say let's check to see where we're at, how are we feeling? The 8, we are feeling great. 8 is great. We can integrate that. Sine 3 theta, that's great. We can integrate that. Sine squared of 3 theta, not quite great. Not terrible, but we're not quite feeling it just yet. So we say, okay, how do we handle that piece? Well, the main thing we're going to use is to say, there's trig here. And trig has wonderful things. One of the most wonderful things about trig is that if you say, look, I don't like the way it's written, there is another way to rewrite it. Now, one of the challenging things about trig is that there's a lot of ways to rewrite it. And so sort of the question like, how do you find the right way? But there's just a handful of units which turn out to be particularly useful. And one of them, spoiler alert, formula sheet, says, sine squared of x is 1/2 1 minus cosine 2x. Or to put it another way, 2 sine squared of x is 1 minus cosine 2x. Okay, now that's useful, because what do we have here? We have a sine squared, but not of x, of 3 theta. That's no problem. Just replace your x by 3 theta. So this becomes 1 minus cosine of 2 times 3 theta, which is a 6 theta. All right, so we're going to update. So then we'll be in our happy place. So we have, so let's be careful here. This is going to become 1 minus cosine 6 theta. And integral 0 to pi over 2. The 1 and the 8, we can put those together to make 9. Minus cosine 6 theta, and then plus 8 sine 3 theta. All right, that's our computation. And all of these now are happy integrals. So we're in our home stretch. We just need to evaluate these pieces. All right, what's the integral of 9? It is 9 theta. What's the integral of cosine? Positive sine. So we're going to have a sine. It'll be 6 theta. And then don't forget to account for that 6 on the inside. And you account for a multiple by dividing by that. You can always check it, right? Just think about taking derivatives. Derivative of 9 theta is 9. Derivative of 1/6 sine 6 theta will be 1/6 cosine 6 theta times 6, and that cancels the 6. All right, how about this one? What's the integral of sine? Negative cosine, right? Be careful. And then you got to account for that 3. And we do it by dividing by 3. All right, and we're almost done. We're going 0 to pi over 2. So, plug in pi over 2. We get 9 pi over 2. Nice. Then we get minus 1/6 sine 3 theta minus 8/3 cosine 3 pi halves. Okay, so we have that. And then subtract, plug in 0. So we get 0 minus 1/6 sine of 0 minus 8/3 cosine of 0. Now some terms just go away. And, oh, whoops. Why did I put a theta there? That should be a pi. Apologies. Half the terms just disappear automatically. The 0, gone. The sine of 0, gone. And sine of 3 pi, if you think about the circle, sine of 3 pi says you're over here. The y coordinate is 0, gone. So those terms are all gone. Now what about cosine 0? Cosine 0, that's 1. So that's not going anywhere. How about cosine 3 pi halves? Now cosine 3 pi halves, that's going to be down here. What is the cosine of 3 pi halves? Oh, good news. That's also gone, right? Oh, an extra term goes away. Phew, I thought it might not go away, but it does. Nice! Yay us! Yay us! All right, cool. Right, the x-coordinate at the angle 3 pi halves is 0. So that leaves us with, we have 9 halves pi minus minus plus, and then 8/3. Okay, and that's our answer. There we go. There we go. All right, and that brings us to number 10. Our last problem. A storage tank is shaped like a right square pyramid. Okay, and square pyramid basically says cross sections are squares. That's going to be very useful for us. It has a height of 4 feet, so up and down, and a base of side length of 2 feet. Now the bottom half of the pyramid, and so it's very explicit here, so this is from height h equals 0 to h equals 2 is water. From h equals 2 to h equals 4 is gasoline. Okay, so the bottom half is water, and this has a density of 60 pounds per cubic foot. The top half is gasoline. This has a density of 40 pounds per cubic foot. And now the question. Calculate the total work required to pump all the water and gasoline to the apex of the pyramid. All right. Well, Now, as I look at this problem, I guess they've already given us height in terms of putting height 0 down here, height 2 up here, and height 4. It's actually going to make it slightly harder. It turns out that when you're doing a pumping problem, it's very convenient to put where you're pumping to as your 0. And so normally I would put the 0 up here. We could change that, but I'll go ahead and do it the way the problem has been phrased, and I'll just grumble about it. Okay, so here I'm going to grumble for a second. Okay, all right. Got my grumbling out. And now we'll just go through and work it out. One thing that will be convenient, and this often happens when you have shapes like this, in particular triangle-like shapes involved, is to slice up and down. So when we look at a cross section here, right? So this is a height equals 4. Here's height equals 0. One thing that I'm very interested in is to understand the distance across. So, 2 by 2 at the bottom, but what would it be at any intermediate point? So at the bottom, we're 2 across, but what if we're here? What is this distance across? So how can we find it? Well, what we can do is we can say this is at an arbitrary height, h, and we look at similar triangles. So the triangle upstairs, this small one, is similar to the triangle of the whole thing. Now, for upstairs, the distance from the tip down to h is 4 minus h. So we say, well, 4 minus h is to this unknown length, as 4, the whole distance, is to 2. Okay? That seems very reasonable. Now what we can do is we can just swap these two locations, right? So we say, oh, the length divide by 2, that's 1/2 4 minus h, or that's 2 minus 1/2 h. And you can check to see, is it reasonable? At h equals 0, we get 2. At h equals 4, we get 0. All right, so that's the side length if we just sort of come up and say, okay, what's, how big, how far across is that? That's the answer. All right, now that's going to be important because let's talk about our generic formula. Our generic formula for work when we talk about pumping, right? Because we got to pump it up, pump it. All right, our work is we're going to add up the work of each sort of cross section. So we have this sort of thin layer, and we're saying, okay, move that up. So it's start to stop. You have your density. You have your depth. You have your area. And you have your thickness. Really, area times thickness is volume. And if you're saying, wait, does this work? One thing you can always do is there's a sanity check called check the units. So work, by the way, when you get work out, the units should be foot-pounds. And so if you think about density, well, that's pounds per cubic foot. Depth is a foot. Area, foot squared. And a thickness is a foot again. And if you multiply through, you'll see that your units become, there's a pound, and then there's a bunch of foot terms canceling, but it becomes a foot-pound. So the units give you a good sanity check to say, hey, does this all mash well? Does this make sense? Because if it doesn't make sense, we shouldn't be doing it. We're going to split this into two parts. So let's talk about our pieces. So we'll start with the water. So we're going to go 0 to 2, right? H equals 0 to H equals 2. Our density is 60. Our depth. Well, our depth is up to our apex. So if we're at H, and here we're at 4, our depth is 4 minus H. And again, this is when it would have been so much easier if they put 0 at the top, but okay, we deal with it. What is our area? Well, our area is a square. And notice here, we can just come back in this form. So it's 1/2 4 minus H squared. And finally, what's our thickness? Our thickness is dH. Okay, well, this here, so this is the water. Well, the 60 squared comes a quarter, times 60 comes 15. Then we're going integral 0 to 2 of 4 minus H cubed. Now, we don't actually have to integrate, so we don't have to expand 4 minus H cubed. I mean, we could, but that would probably give us some heartbreak. Instead, we just say, look, use substitution or just know how integration works. Hopefully, we just know how integration works. So this becomes 15. Now, when we integrate, we're going to add a 3 here and add 1 to the 3 and divide. So that's a 1/4. And we're going to have 4 minus H to the 4th power. And then we have to compensate for that minus on the inside. And so we're going to add a minus in front. And evaluate from 0 to 2. Okay, so what does that give us? Well, when we plug in 2, we get 4 minus 2, which is 2. 2 to the 4th is 16 times a 4th. So this is minus 15 times 4, right? 2 to the 4th is 16 times a 4th. Yeah, that checks out. When we plug in 0, so we subtract, but there's a negative, so that makes a plus. 15, and then we have 1/4 times 4 to the 4th. Well, 4 to the 4th is a big number. We can cancel off a 4, and that becomes 4 cubed, and that's 64. Okay, well, that's still a big number. 4 to the 4th is 256. All right, and, well, what can we do? Well, this is the same as 15. Pull it out. Take 64, subtract 4 times 60, and 15 times 60 gives us 900. So that's just the water. Now, that's going to be the big part because, 1, water is heavier, 2, there's a lot of it, and 3, we have to move it further. So that's going to be the big piece. Okay, so that's the water piece. We're not done yet. We also have to do the gasoline. Okay, so for gasoline, Now, the good news is we've done the work. We just have to basically make the modification. Now we're 2 to 4. 2 to 4. Our density is 40. So it's easier. Our depth is still the same. Our area is still the same. And our thickness is still the same. So 1/4 squared is a quarter times 40 gives us 10. Okay, so we have 10. And then we have the integral 2 to 4 of 4 minus h cubed. It's the same integral other than the constant in the front. Okay, so carrying that integral out, well, we're going to get that minus like we did before, that 10, and that 1/4 times 4 minus h to the 4th, evaluated from 2 to 4. When you plug in 4, though, what do you see? 4 minus 4 is 0, so we get a 0. Subtract. But there's a minus, makes it a plus. Then we have 10 times 1/4 times 2 to the 4th. Okay, well, 2 to the 4th is 16 times 1/4 is 4. So 10 times 4 equals 40. So that's a much smaller number. But like we said, there's a lot less, it's lighter, and you don't have to move it as far. So that's the work to move the gasoline. So what's the total work? Well, the answer is you put these two together. So our total work is 940 foot-pounds, right? 900 plus the 40. Whew, that one was a bit of a workout. If you do change to putting 0 at the top and 4 at the bottom, it'll make the computation slightly easier, but the process is, for all intents and purposes, the same. Well, we took a good chunk of time, but we did finish in less than 75 minutes, so that's a good sign. And we said a lot. And so when you're taking the test, you don't have to say as much. Pace yourself. You can do this. You're here. Go for it. Believe in yourself. Put in the time. Put in the practice. You can succeed. I believe in you because you are great. And I hope you do great on your test. All right. Thanks for joining me. And I hope I get to see you again. Bye.